Hey guys, welcome to Quick Science. Today I'm going to talk about three topics: the combined gas law, the ideal gas law, and Dalton's law. Without further ado, let's get started. The combined gas law, as its name states, is the combination of the three laws. The first law being Charles' law, the second law being Boyle's law, and the third law being Gay-Lussac's law. Now, what do all of these letters mean? P stands for pressure, V stands for volume, and T being temperature. The numbers 1 and 2 are the initial and the final states. The standard unit of pressure is atmosphere. The standard unit of volume is liters or milliliters, etc. And lastly, the standard unit of temperature is Kelvin, degrees Celsius, or degrees Fahrenheit. It is a true constant if the numbers of moles of the gas doesn't change. Now I'm going to give 5 examples to further explain what I mean. Let's now head to example number 1. A sample of sulfur dioxide occupies a volume of 652 milliliters at 40 degrees Celsius and 720 mmHg. What volume will the sulfur dioxide occupy at standard temperature and pressure? Now, what I like to do when solving equations is to first identify all the values. So, our volume 1, or our first value of the volume, is 652 milliliters. 652 milliliters. Now, our next value, 40 degrees Celsius, is our initial temperature. Remember what I told you earlier about the standard units of temperature? Well, in this case, we need to use Kelvin. And to convert it to Kelvin, we need to add 273.15 Kelvin. So, get your calculator and calculate with me. So, the answer is 313.15. Let's now look at our initial pressure, which is 720 mmHg. We then look to our next units of pressure, or the final units of the values pressure. So here, our standard temperature and pressure. Our standard temperature is 273.15 Kelvin, since Kelvin is our standard unit here. And we need 273.15 to add it in order to convert things like degrees Celsius, blah blah blah. Now, our standard pressure is supposed to be 1 atmosphere. But since our initial pressure is mmHg, let's convert it to mmHg2, which is 760 mmHg. Let us now identify what we are finding in this equation. And we're finding the final volume of this equation. Now, what we need to do next is to write the formula, which is P1V1 over T1 equal to P2V2 over T2. Now, let us derive this formula. First, in deriving from fractions, we need to do the multiplying crossover method, where we multiply P1V1 with T2 to P2V2 with T1. Then, what are we finding? Volume 2. So, we need to erase these two values here in order to get only volume 2. So, divide both sides then P2T1, P2T1. You can now see that this can be cancelled. So this is our equation in finding the volume 2. Now, in order to get the solution, we just need to replace these with the values we have got. So our P1 is 720 mmHg. Our V1 is 652 ml. And our temperature 2 or T2 is 273.15. 3.15 Kelvin. Then our P2 is 760 mmHg. And our T1 is 313.15 Kelvin. Now, what we need to do here, since we're finding volume 2, we need to cancel these values because it's a fraction and they're going to be cancelled. Now, our final answer is 538.78, rounded off to 2 decimal places, milliliters. So, we have now solved the final volume of this first example. Let's move on to the next so that you can really get this into your head and to understand it more. So, welcome to the second question. 322 liters of hydrogen occupies a volume of 197 liters at standard temperature and pressure. If the initial temperature of the hydrogen was 37 degrees Celsius, what was its initial pressure? So again, as I stated earlier, we need to list down all of the values that we get from the problem. So our first value, volume 1, is 322 liters. Our next value is volume 2, or final volume, which is 197 liters. Now, as you can see, this in the problem, this part of volume 1 standard pressure, that's the final units to occupy a volume of 197 liters. So, our final units are the standard temperature and pressure. So, our standard temperature is 273.15. Out of all my problems, I'm going to use the standard unit of Kelvin so that you can better grasp what I'm talking about. Then, our next value is standard pressure, which is ATM, 1 ATM. So, what we will now do next is to write the initial temperature, which is 37 degrees Celsius. Now I'm going to convert it to Kelvin, 310.15 Kelvin. So, what are we looking for in the problem? It's our initial pressure. Initial pressure, P1. We then go to our formula, P1 V1 over T1 equal to P2 V2 over T2, and we do the derivation again, which is we cross multiply P1 V1 T2 equal to P2 V2 T1. Then what are we looking for? Initial pressure. So in order for this to be only on this side, we need to divide both sides by V1 T2. V1 T2. Now, our derived formula is P2 V2 over T1 over V1 T2 is equal to the initial pressure. Now, again, we need to replace the values to our derived formula. So, P2 is 1 atmosphere. V2 is 197 liters. And temperature 1, or initial temperature, is 310.15 Kelvin. We then divide it by V1, or 322 liters, times temperature 2, which is standard temperature, 273.15 Kelvin. Now, again, so our answer is 0.69 atmosphere. That is our initial pressure. Now, on to our third question. A sample of argon has a volume of 5.0 decimeters cubed and the pressure is 0.92 atmosphere. If the final temperature is 30 degrees Celsius, the final volume is 5.7 liters, and the final pressure is 800 mmHg, what was the initial temperature of the argon? So, what you first do is, again, you need to find the values in the problem. So, our first value, V1, or initial volume, is 5.0 decimeters cubed. Our next value is our initial pressure, which is 0.92 atmosphere. Our third value, we can then see, is final temperature, which is 30 degrees Celsius. Now, again, we're going to convert it to Kelvin because that's our standard unit of temperature. 273.15 Kelvin. Our next value is our final volume, which is 5.7 liters. And the final temperature, the final pressure is 800 mmHg. What is the initial temperature? Now, as you can see in this problem, we have to first make the values the same to one another so that we can cancel it in our final solution. Now, as you can see, our volumes are different. Decimeters cubed, liters. So, to convert decimeters cubed to liters, all you have to do is to simply multiply it by 1. Then, our pressures are atmosphere or mmHg. You can either choose what you're going to use for this equation, but since our standard unit right now we're using is atmosphere, we're going to use atmosphere. So 800 mmHg, we're going to convert it to atmosphere. So 1 atmosphere. Now 1 atmosphere is equivalent to 760 mmHg. Now what we do is we cross this out, 0.0526 when measured up to 4 decimal places. Now, what we're going to do is to derive the formula. Now, what we're looking for is initial temperature. So let's write our formula again. Then, since they're fractions, we're going to do the crossover method, the cross multiplying method. P1 V1 T2 go to P2 V2 T1. Then we're looking for initial temperature. So we need to divide it again by P2 V2 in order to have only temperature on this side, and to get rid of this P2. So our formula for temperature 1 is P1 V1 T2 over P2 V2. So what we need to do now is to replace the values with our formula. So P1 is 0.92 atmosphere. V1 is 5 liters, and T2, final temperature, is 303.15 Kelvin. We then divide this to our denominator. Our P2 is 1.0526 atmosphere, and our V2 or volume 2 is 5.7 liters. Again, we need to cross out this so that our answer will have only for temperature, which is Kelvin. So our final answer is 232.42 Kelvin. Now let's head over to our fourth example. The initial temperature of a 1.00 liter sample of argon is 20 degrees Celsius. The pressure is decreased from 720 mmHg to 360 mmHg, and the volume increases to 2.14 liters. What was the change in temperature of the argon? So first, like I stated earlier, we need to write our values in the problem. So our first value is the initial temperature of 20 degrees Celsius. Our next value is our volume 1, which is 1.00 liters. Our next value is our pressure 1, which is 720 mmHg. Sorry. Our pressure 2 is 360 mmHg. And then our volume 2 is 2.14 liters. After that, we then look at what we're finding in our problem. So what we're finding is the change in temperature, or the temperature 2. Temperature 2. So again, let us derive our formula. But first, we need to convert this to Kelvin. So 20 plus 273.15 Kelvin. 3.15. Then, we do the derivation of the formula. So, our formula is P1 V1 over T1 equal to P2 V2 over T2. We then do the cross-multiplying method. P1 V1 T2 equal to P2 V2 T1. Then, what we're finding is our final temperature. So, let's divide both sides by P1 V1 because we only need our final temperature in our solution. So, this is the formula of our final temperature, which is P2 V2 T1 over T1 V1. We then substitute the values we've got with our formula. So our P2 is 360 mmHg. Sorry for the marker, I'm just having a hard time here. 60 mmHg. Our V2 is 2.14 liters, and our T1 is 293.15 Kelvin. Then our denominator is P1 720 mmHg and V1, which is 1.00 liters. So what I do first is we're going to cancel this. Cancel. Then we're going to solve the formula. 313.67 Kelvin. That's our final answer. So this is our last example. A sample of nitrogen gas occupies a volume of 2.00 liters at 756 mmHg and 0.00 degrees Celsius. the volume increases by 2.00 liters and the temperature decreases to 137 Kelvin. What is the final pressure exerted on the gas? So again, we need to list down all of the values we see in the problem. So our volume 1 is 2.00 liters. I'm sorry for the markers. Okay. Our pressure 1 is 756 mmHg. Wait, I'm just going to clean this out. And our temperature 1 is 0.00 degrees Celsius. But as I'm saying, we're going to use Kelvin. So we need to add 273.15 Kelvin, which is just 273.15 Kelvin. Then, it says that our volume increases by 2.00 liters. So we just need to add 2.00 liters to 2.00 liters. So our volume 2 is 4.00 liters. Then our temperature 2 decreases to 137 Kelvin. Temperature to 137 Kelvin. Then our final question is, what is the final pressure exerted on the gas? So again, we need to derive our formulas first. So P1 V1 over T1 is equal to P2 V2 over T2. Now again, like I taught you earlier, we're going to derive this formula by doing the crossover multiplying method. P1 V1 T2 is equal to P2 V2 T1. And then, what are we looking for? The final pressure. So it's P2. We're then going to divide both sides by its remaining values in order to cancel them out. So our formula for our final pressure is P1 V1 T2 over V2 T1. Now, we will then replace the values with our formula. So our P1 is 756 mmHg. Our V1 is 2.00 liters, and our T2 is 137 Kelvin. Then we divide it to our denominator, which is V2, 4.00 liters, and our T1, which is 273.15 Kelvin. Then what we do is we cancel out the values, the standard units, and then come to our final answer. Our final pressure is 189.59 because it is rounded off to 2 decimal places. mmHg. The ideal gas law relates the pressure, volume, gas constant, and temperature of gases. Now, while it describes the behavior of hypothetical gases, it also describes the behavior of real gases in real situations. Now, I've already taught you what is pressure, volume, and temperature. But what is the gas constant? So, the gas constant is the standard constant of gases, the standard number of gases in an equation. It can also be found by deriving this equation, in which it is PV over NT. That's how we get the gas constant. We use this formula in order to get the ideal gas in different situations. Now, I'm going to give 5 examples again of this equation. Now, let's head over to our first example. If I have 4 moles of a gas at a pressure of 5.6 atmosphere and a volume of 12 liters, what is the temperature? So, keeping the formula in mind, first you need to write all of the values that enlist in this problem. So, the first value that I see is 4 moles. So, Rn is 4 moles. Then, the second value I see is 5.6 atmosphere. So we're going to write in pressure 5.6 atmosphere. Then the next value I see is 12 liters. So we're going to write in volume 12 liters. Now, where's the gas constant? Like I said earlier, it is a constant. So we just need to write what I wrote earlier, which is 0.0821 liters times atmosphere over moles times Kelvin. Because, like I said it earlier, it's a derived formula of PV over NT. Then, of course, what's missing? That is the pressure. So, we're gonna write, the temperature. So, we're gonna write T equals question mark because we haven't found the solution yet. Then, after that, we then write our equation in order to derive it. So, PV is equal to nRT. Now, since they're already equal to both sides, what are we finding? Temperature. So let's just divide both sides by nR. So, the formula for temperature is PV over nR. Now, let's look at our values and replace them with the formula. So, P is 5.6 atmosphere. V is 12 liters over N is 4 moles and R is 0.0821 liters times atmosphere over moles times Kelvin. Now, we need to cancel out all of the values in order to get only Kelvin. Cancel out all the standard units in order to get only Kelvin. So, mole, mole, atmosphere, atmosphere, liters, liters. So, our final answer is 204.63 rounded to the second place, the 10th place. So, Kelvin, this is our final answer. So, the second example is, if I have an unknown quantity of gas at a pressure of 1.2 atmosphere, a volume of 31 liters, and a temperature of 87 degrees Celsius, how many moles of gas do I have? So, again, first, we have to write all of the values that we see in the example. So, our pressure is 1.2 atmosphere. Our volume is 31 liters. And our temperature is 87 degrees Celsius. And of course, our gas constant is 0.0821 liters times atmosphere over moles times Kelvin. How many moles of gas? So moles. How many moles of gas? So again, first is to derive the formula. PV is equal to nRT. Since moles are what we are finding, we have to divide both sides by RT in order to cancel this out and to have only moles on that side. So PV over RT is equal to N. Now, we need to replace the values in this derived formula. So our P is 1.2 atmosphere. Our V is 31 liters. Our R is 0.0821 liters times atmosphere over moles times Kelvin. And our temperature is, wait, I forgot that in temperature we have to convert this to Kelvin in order to cancel it Kelvin out. So we need to add 273.15 Kelvin. Now we write this in here, 360.15 Kelvin. Lastly is to solve the formula. But first, we need to cancel out all of the values in the fraction. I mean in the equation. So atmosphere, liters, Kelvin. Final answer is 1.26 moles. So, our third example is, if I contain 3 moles of gas in a container with a volume of 60 liters and at a temperature of 400 Kelvin, what is the pressure inside the container? So, as I said earlier, we're going to list all of the values that we see in the problem. So, our N is 3 moles. Our volume is 60 liters. And our temperature is 400 Kelvin. Our gas constant being 0.0821 liters times atmosphere over moles times Kelvin. And now, what are we looking for? That is the pressure. So pressure equals question mark because we haven't found the answer yet. Now, we need to derive in order to get the pressure from the formula. So PV is equal to nRT. And that's simple. We just need to take this V off of this equation. I mean this side. So we just need to divide both sides by V in order to balance the formula. And now we have nRT over V. That's our formula for pressure. Now, let's substitute all of the values we've got with the formula. So, our N is 3 moles. Our R being 0.0821, our constant. And our T being 400 Kelvin over V, which is 60 liters. So, our final answer is 1.64 atmosphere. Because atmosphere is the standard unit of pressure. Our fourth example is, if I have 7.7 moles of gas at a pressure of 0.09 atmosphere and at a temperature of 56 degrees Celsius, what is the volume of the container that the gas is in? So, let's list all of the values that we see in the problem in order to set them for our derived formula, which is we'll do later. So, our moles is 7.7. So you can see here, our pressure is 0.09 atmosphere. And our temperature being 56 degrees Celsius. And as I said earlier, we need to convert this to Kelvin in order to cancel it out in the gas constant. So 273.15 Kelvin. our gas constant being 0.0821 liters times atmosphere over moles times Kelvin. And what are we looking for? That is the volume. So I'm going to put a question mark here because we haven't found the answer yet. Now, let's derive the formula. So PV is equal to nRT. We're looking for volume, so we need to cancel out this P here. So let's divide both sides by P in order to cancel it out here and to balance the whole equation. So V is equal to nRT over P. Now, again, let's replace the values in the formula. So N is equal to 7.7 moles. Our R being 0.0821 liters times atmosphere over moles times Kelvin. And our temperature being 329.15, Kelvin over our P being 0.09 atmosphere. So our final volume is 2,311.99 liters. Oh wait, I forgot that we have to cancel this out first. So moles, atmosphere, Kelvin, leaving us only with liters. So this is our final answer. Let's now head over to our last example. If I have 1.9 moles of gas held at a pressure of 5 atm and in a container with a volume of 50 liters, what is the temperature of the gas? So, you first need to write all of the values that you see in the equation, in the problem. So our first value is moles, and it is 1.9. So, 1.9 moles. Our next value is pressure, which is 5 atm. So pressure 5 atm. And our next value is the volume, which is 50 liters. 50 liters. And our last value is the gas constant, which is 0.0821 liters times atmosphere over moles times Kelvin. Now, what we are looking for is temperature. So let's derive it in the equation. PV is equal to nRT. Now, what we need to find is temperature. So we need to divide both sides by nR to erase this and to balance the equation. So temperature is equal to PV over nR. Pressure times volume over moles times gas constant. Now, all we need to do is to substitute it into the formula. So Rp is 5 atmosphere. Rv is 50 liters over Rn, which is 1.9 moles, and Rr, which is 0.0821 liters times atmosphere over moles times Kelvin. Our final answer, or our final temperature, our temperature is, but first we need to cancel out all of the standard units so that all we have left is Kelvin, and 1602.67 Kelvin. This is our final answer. We're waiting for you, my love. So this is the final law that I'll be talking about, and it's Dalton's law of partial pressures. This law states that the total pressure of a mixture of gases is the sum of those component gases, of the partial pressures of those component gases. And you can see in this formula that in order to get the total pressure, you just have to add the components. And this is symbolized by A, B, and C. And The next formula is PA is equal to XAP total. What does this mean? This formula is just the formula for the partial pressures if there is a missing partial pressure of that gas. And what we need to do is just to multiply the mole fraction or the fraction of moles with the total pressure of the gas. In here, you can see this is the formula for the mole fraction, which is the number of moles over the total number of moles of every gas. Now, in order to get those moles, we just need to divide the weight of the gas with the molar mass. And this is when this formula comes into play, where in a problem, when it is stated that grams is a given formula, then you just need to convert it to moles and to derive it from the ideal gas law formula, which is PV nRT. PV is equal to nRT. But here, it is where you divide it from the volume of each of the gas. So if you're confused about what I just said and what I just wrote here, I'm going to give 5 examples to further teach what I want to tell you and to further discuss what is that I am saying. Let's now head over to our first problem. A container contains 3 gases, nitrogen, oxygen, and argon, with partial pressures of 23.3 kPa, 40.9 kPa, and 13.7 kPa respectively. What is the total pressure inside the container? So, first, we need to write all of the values that we see in the problem in order to come up with the formula. So, we see that the partial pressure of nitrogen is 23.3 kPa. The next thing that I see is the partial pressure of oxygen, which is 40.9 kPa. And the last partial pressure I see is the partial pressure of argon, which is 13.7 kPa. Now, we can now look at the question, which is what is the total pressure inside the container? So, we can, as I analyze the problem, I can see that we can use the first formula, which is P total is equal to PA plus PB plus PC. Because the question states that what is the total pressure inside the container. And I can see that it gave all 3 pressures. So we just need to sum it up. So PN2 plus PO2 plus PAR is equal to P total. We can then substitute the values of this into our formula. So PN2 is 23.3 kPa plus PO2 is 40.9 kPa and PAR is 13.7 kPa. So we just need to add these 3 values and we can come up with the answer of 77.9 kPa, which is the total pressure that we needed to find. Now, let's head over to our second question. In the chem lab, a student filled a balloon with 2 different gases, carbon dioxide and nitrogen. The atmospheric pressure in the chem lab was 770.0 mmHg, and the partial pressure of CO2 added to the balloon was 0.3255 atm. What was the partial pressure of N2 in the balloon? So again, the first thing we need to do is to write all of the values that we see in the problem. So the first value I see is the atmospheric pressure or the total pressure in the chem lab. So the total pressure in the chem lab was 770.0 mmHg. Then I see that the partial pressure of carbon dioxide was 0.3255 atm. But wait, let's look at these given examples. We can see that the unit of pressure of them is different. But in order to get the right pressure in this situation, we need to look at the total pressure. So the total pressure is mmHg. So we need to convert this atm to mmHg. So when you're converting something, you put 1 and then the unit you want to cancel in the denominator, and you put the value it is equated to in what you want it to be converted to. So let's cancel this out. 247.38 mmHg. So that is our converted pressure. Then what is missing? The partial pressure of N2. So instead of getting the total pressure, we need to get a partial pressure. So what we do in this equation is to just derive the formula. So P total is equal to PCO2 plus PN2. But what we're looking is PN2. We just need to transpose CO2 to the other side. So, and to change its symbol. So PT minus PCO2 is equal to PN2. Why? Because PT is the total pressure. If you just subtract a partial pressure from it, the remaining partial pressure of that is our answer. So we then substitute our values. So our P total is 770.0 mmHg. And our CO2, our partial pressure, is 247.38 mmHg. Our final answer should be 522.62 mmHg. And that is how you use the first formula. Let us now head to our third example. A storage tank contains 4 moles of helium, 2 moles of oxygen gas, and 8 moles of nitrogen gas at a total pressure of 3000 torr. What is the partial pressure of each gas? So let us first now look at the values we see in the problem. So our first value that I see is 4 moles of helium. So let's put Na is equal to 4. Right, the next value I see is 2 moles of oxygen gas. So let's put Nb is equal to 2 moles. Moles. The third value I see is 8 moles of nitrogen gas. So let's write Nc is equal to 8 moles. A, B, and C are just representing the given values I see in the problem. Now, what we do is, since the question is what is the partial pressure of each gas, we need to write first the total pressure. Forgot. So the total pressure is 3000 torr. So, well, what we must first do is to look at the formulas that we need to use. So we'll use the second formula. P is equal to mole fraction times PT, because we are looking at the partial pressures in this example. Next is we need to use the formula of mole fraction, because if we don't use the formula of mole fraction, this formula wouldn't be useful too. So it's Na over N total. Now, since our given is already here Na, Nb, and C, we first need to A represents helium, B represents oxygen, and C represents nitrogen gas. Now what we must first do is to substitute it with the formula, which is Xa is equal to 4 over 4 plus 2 plus 8, because these are the total moles of this equation. Now we need to solve it. So 4 over 14 is 0.2857. Xb is equal to Nb over Nt. So our Nb is 2 and our Nt is still 4 plus 2 plus 8. So 2 over 14 is 0.1428, 0.1429, and our mole fraction of C, or nitrogen, is 8 over 4 plus 2 plus 8. So 8 divided by 14 is 0.5714. Now, to check if our solution is right, if we add these values, it must always equate to 1. After that, after we get the mole fractions, you just need to multiply it with the total pressure. So 0.2857 times 3000 torr is 857.1. Next is torr. Next is 0.1429. So 0.1429 times 3000 torr is 428.7 torr. And our last partial pressure is 0.5714 times 3000 torr. So it is 1714.2 torr. Now, to check if our answers are right, we need to make sure that if we add them to one another, what we get is 3000 torr. So let's double check. So P total is equal to 857.1 plus 428.7 plus 1714.2 is equal to 3000. So all of these are correct. Now this is the third example. Let's now head to example number 4 to further make you understand the second formula. So a tank contains 7 moles of neon gas and 9 moles of helium gas at a total pressure of 2500 kPa. What is the partial pressure of each gas? So again, we need to find the given values in our equation. So the first value I see is 7 moles of neon gas. So let's just put Pa to represent neon gas and 7 moles. The next value I see is 9 moles of helium gas. So let's put B as a representative and put it as 9 moles. Now, what we do here again is to use the mole fraction formula first. So it's XA equal to NA over NT. So, first, oh my god, I'm sorry, this is NA and NB. So, first is that we have to substitute it with the formula. So, Na is 7 moles. And again, the N total is just the sum of all moles. So, 7 plus 9. So, 7 divided by 16 is equal to 0.4375. We then use the formula on B. Just replace A with B. So 9 over 7 plus 9 is equal to 0.5625. After that, we use this formula, which is PA is equal to XA times P total. So, we're just going to multiply it with the total number, with the total pressure in this equation. So, 0.5625 times 2,500 is equal to 1,406.25. Now, let's use this. 0.4375 times 2,500 is equal to 1,183.75 kPa. So in order to check these two, we just need to add this together. So I just tried to calculate it, and my calculations were wrong. This is supposed to be 1,093.75. So this is the last, but definitely not the least, example in this law. So we'll be using the third formula. So 18 grams of neon gas and argon are mixed in a 1 liter container at 350 Kelvin. Calculate the partial pressure of each gas and the total pressure. So the first thing we need to do is to put all of the values you see in the problem. And since I see 18 grams of neon gas and argon, we're going to use weight because we're using the unit grams. So the weight of neon is 18. And we can see that neon and argon are mixed, so both of them are 18. Then I see the volume, which is 1 liter. Sorry. And I see the temperature as 350 Kelvin. Now, why are we using the third formula? This is because we can see it in the given values that we're going to use volume, temperature, and moles. But this is the weight, and we need to convert it to moles. And even though it's not given, we're going to use the constant gas value, which I discussed earlier. That is 0.0821 when rounded off to 4 decimal places. 0.0821 liters times atmosphere over moles times Kelvin. Then we write the third formula, which is PT is equal to NA RT over V plus and B RT over V, because we have two given values. So first, what we need to do is to convert weight to moles. So that we can use this equation, because we can't see any weight here. So N is equal to weight over molar mass. So the weight of neon is 18 grams, and we then get the molar mass of neon, which is 20.1797, 0.8920 moles when rounded off to 4 decimal places, because we're using it in a equation. Now, let's divide argon by its molar mass, which is 39.940, 0.4507 moles. Now that you've converted it to moles, we then use this equation. So PT is equal to Na, RNA, RNB, RNA being 0.8920 moles, times our gas constant, which is 0.0821 liters times atmosphere over moles times Kelvin, and our temperature, which is 350 Kelvin, over 1 liter. We then cancel liters, cancel moles, and cancel Kelvin, so that atmosphere is the one left. So I'm just going to solve this. So our partial pressure of neon is 25.63 mmHg. Then we get the partial pressure of argon. So I used mmHg just as an example, but you can use stuff like kPa, torr, etc. Then let's do the partial pressure of argon. So I'll just erase this. And put the example. So PB. So our Na of argon is, our moles of argon is 0.4507. Sorry for the handwriting. Moles. Our gas constant being 0.0821 liters times atmosphere over moles times Kelvin. And our temperature being 350 Kelvin all over 1 liter. After that, we cancel the standard units, mole, mole, Kelvin, Kelvin, so that atmosphere is left. And our answer, our gas constant in argon, our partial pressure of argon is 12.95 mmHg. Now, as I thought earlier, to get the total pressure, you just need to add the partial pressures in the equation. So P total is equal to PA plus PB. So our total pressure NNHG. And that's it for Dalton's law. So hey guys, thank you for sticking with me until the end of this video. I'm sorry for it being a little long and boring and lots of background sounds, because this is my first time doing a YouTube video and I don't have the right equipment to do a really good one. So thanks for watching. I hope you learned a lot, and I'll see you guys later.